Tonight, we're going to explore something that keeps astronomers awake at night. Not the beauty of distant galaxies or the elegance of orbital mechanics, but the genuinely terrifying discoveries lurking in the cosmic darkness. Things that challenge everything we thought we knew about our safety in this universe. Things that make us realize just how fragile our existence really is. We're talking about invisible predators wandering through space, quantum catastrophes that could erase reality itself, and ancient cosmic riddles whose answers might doom us all. This isn't speculation or theory. These are real phenomena observed by real scientists using real instruments, and some of them could end everything tomorrow without warning. By the end of tonight, you're going to understand why the universe isn't just awe-inspiring, it's genuinely frightening in ways that most people never consider. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something that sounds like science fiction, but is absolutely real: rogue black holes. Black holes wandering through space with no fixed orbit, no predictable path, just drifting through the galaxy like cosmic predators in the dark. Most black holes sit at the centers of galaxies, anchored by billions of stars orbiting around them. These supermassive black holes are terrifying in their own right, but at least we know where they are. They're predictable. They stay put. But not all black holes follow this pattern. Some black holes are stellar mass black holes formed when massive stars explode as supernovae. These typically weigh between 3 and 100 solar masses. That's 3 to 100 times the mass of our Sun, compressed into a sphere maybe 19 to 186 miles across. And here's the terrifying part. Many of these stellar mass black holes don't stay where they formed. Gravitational interactions with other objects can send them wandering. A close encounter with another star or black hole can change its trajectory, essentially ejecting it from its birth location and sending it on a journey through the galaxy. These are rogue black holes, and astronomers estimate there could be hundreds of millions of them in our galaxy alone. Think about that number for a moment. Hundreds of millions of invisible objects, each one capable of catastrophically disrupting anything that gets too close, wandering through space with no warning, no visible sign of their presence. Black holes don't emit light. They're defined by the fact that nothing, not even light, can escape their gravitational pull once it crosses the event horizon. This makes them essentially invisible unless they're actively feeding on nearby matter. When a black hole pulls in gas or stars, that matter heats up to millions of degrees and emits X-rays that we can detect. But a rogue black hole traveling through empty space between stars isn't feeding on anything. It's completely dark, completely invisible, moving through the galaxy at speeds of hundreds of miles per second. You wouldn't see it coming. The invisibility of these objects makes them uniquely terrifying. With asteroids or comets, we can see them coming years or decades in advance. We can track their orbits, calculate their paths, and potentially take action to prevent a collision. With a rogue black hole, we'd have no such luxury. The first sign of a rogue black hole approaching our solar system would be gravitational effects on distant objects. Astronomers might notice perturbations in the orbits of outer solar system objects, comets deviating from their predicted paths, or asteroids being pulled in unexpected directions. But by the time these effects became obvious, the black hole would already be dangerously close. And here's something that makes this even more disturbing. We don't actually know how many rogue black holes exist in our galaxy. The estimate of hundreds of millions is based on computer simulations of galactic dynamics and stellar evolution. Scientists calculate how many massive stars should have formed over the galaxy's history, how many of those stars should have collapsed into black holes, And how many of those black holes should have been ejected from their birth locations by gravitational interactions? The numbers suggest hundreds of millions, but we can't verify this directly because we can't see rogue black holes unless they happen to be feeding on something. There could be far more than we estimate. Or there could be far fewer. We simply don't know. Some rogue black holes might have velocities higher than average, having been accelerated by particularly violent gravitational encounters. These high-velocity black holes would be even more dangerous because they'd spend less time in any given region of the galaxy, reducing the chances we'd detect their gravitational effects before they arrived. A black hole moving at several thousand miles per second could cross the distance from the outer Oort cloud to Earth in a matter of years, leaving little time for detection and absolutely no time for any defensive measures, even if such measures were possible, which they're not. There's another terrifying aspect to consider. Black holes can form binary pairs, two black holes orbiting each other. When massive stars in binary systems both collapse into black holes, they continue orbiting each other, gradually spiraling inward as they emit gravitational waves. Eventually, these binary black holes merge in a violent collision that releases more energy in a fraction of a second than all the stars in the visible universe combined. But before they merge, they form a binary system that can be ejected from its location through gravitational interactions with other objects. A binary black hole system moving through the galaxy would be twice as dangerous as a single rogue black hole. The combined mass would create stronger gravitational effects over larger distances, and the system would disturb objects in the solar system even more dramatically than a single black hole would. And here's something that keeps astronomers up at night. In the centers of galaxies, where stars are densely packed and black holes are more common, gravitational interactions happen frequently. These interactions can accelerate black holes to incredible velocities, sometimes fast enough to escape the galaxy entirely. These are called hypervelocity black holes, and they can be moving at thousands of miles per second. A hypervelocity black hole expelled from the center of our galaxy or from a nearby galaxy could be headed in our direction right now. At thousands of miles per second, it would cross the distance from the galactic center to our solar system in just a few million years, a blink of an eye in cosmic terms. Scientists have detected hypervelocity stars, stars moving fast enough to escape the galaxy, and the same mechanism that ejects stars can eject black holes. We know these objects exist. We just don't know where they all are or where they're going. What happens if one passes near our solar system? The gravitational effects would be devastating long before the black hole arrived. If a stellar mass black hole, say 10 times the mass of our Sun, passed within a few light years of our solar system, its gravity would begin disturbing the orbits of objects in the Oort cloud. The Oort cloud is a spherical shell of icy objects surrounding our solar system, extending from about 2,000 astronomical units to as far as 100,000 astronomical units from our Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So, the Oort cloud extends from about 186 billion miles to 9 trillion miles from our Sun. It's massive, and it contains trillions of icy objects, any one of which could become a comet if disturbed. A passing black hole would gravitationally disturb these objects, sending thousands or even millions of them plunging toward the inner solar system. Earth would face a bombardment of comets, lasting potentially millions of years. Each impact could cause mass extinctions. The dinosaurs were wiped out by a single asteroid about 6 miles across. Imagine hundreds or thousands of similar impacts spread over millennia. Complex life on Earth would almost certainly be destroyed. But that's not even the worst scenario. If the black hole passed closer, within about 1 light year, its gravitational influence would begin affecting the planets directly. planetary orbits would become destabilized. Earth's orbit around the Sun is remarkably stable, varying by less than 2% in its distance from the Sun over the course of a year. This stability is crucial for maintaining Earth's climate and habitability. A passing black hole could change Earth's orbital eccentricity, making our orbit more elliptical. Suddenly, Earth might swing much closer to the Sun during part of its orbit and much farther away during other parts. This would create extreme seasonal variations that would make Earth uninhabitable, or the black hole's gravity could slow Earth's orbital velocity just slightly, causing Earth to spiral inward toward the Sun. Over thousands or millions of years, Earth would gradually get hotter and hotter until the oceans boiled away and the planet became a lifeless desert like Venus. Alternatively, if the black hole's passage increased Earth's orbital velocity, Earth could be flung outward, away from the Sun. Earth would freeze, becoming a rogue planet itself, wandering through interstellar space in eternal darkness. The worst-case scenario is a direct interaction. If a rogue black hole passed within about 1/10 of a light-year, roughly 4 trillion miles, it could gravitationally capture Earth, pulling our planet out of orbit around the Sun entirely. Earth would be pulled toward the black hole, accelerating as it fell. The tidal forces near a black hole are extreme. Tidal forces arise because gravity gets stronger as you get closer to the massive object. If Earth were falling toward a black hole feet first, so to speak, the side of Earth facing the black hole would experience much stronger gravity than the side facing away. This difference in gravitational pull would stretch Earth. At first, the stretching would be subtle, but as Earth got closer, the forces would intensify. Eventually, Earth would be torn apart, ripped into pieces by the difference in gravitational force across its diameter. This process is called spaghettification, and yes, that's a real scientific term. The fragments of Earth would form an accretion disk around the black hole, a spinning disk of superheated debris. Friction within the disk would heat the material to millions of degrees, causing it to emit intense X-rays. From a distance, the death of Earth would be visible as a brief X-ray flare, lasting perhaps a few days or weeks, before fading as the last remnants of our planet disappeared into the black hole. Everything that ever existed on Earth, every person who ever lived, every achievement of civilization, every work of art, every recorded thought, all of it would be crushed beyond the event horizon into the singularity at the black hole's center. So how likely is this scenario? Fortunately, not very likely, at least not in the near future. Space is vast, and even with hundreds of millions of rogue black holes in the galaxy, the chances of one passing close to our solar system in the next million years are very small. Astronomers estimate the risk of a rogue black hole passing within 1 light-year of our Sun in the next billion years at less than 1%. That's reassuring, but it's not zero. The fact that this is even possible, that invisible massive objects are wandering through our galaxy right now, should give you pause. We're safe for now, but on cosmic timescales, it's not a question of if, but when something like this might happen. And there's no way to prevent it. If astronomers detected a rogue black hole heading our way, even with decades or centuries of warning, there would be nothing we could do. You can't deflect a black hole the way you might deflect an asteroid. It's too massive, and it's moving too fast. We would simply have to watch as it approached, knowing exactly what was going to happen and being completely powerless to stop it. That helplessness is perhaps the most terrifying part. Before we move on to our next cosmic threat, let's talk about something that sounds like it belongs in science fiction, but is very real: magnetars. Magnetars are a type of neutron star, with magnetic fields so powerful they defy comprehension. To understand how extreme magnetars are, we need to understand neutron stars first. When a massive star runs out of fuel and explodes as a supernova, the core collapses. If the core's mass is between about 1.4 and 3 solar masses, it collapses into a neutron star. A neutron star is essentially a giant atomic nucleus. The protons and electrons are crushed together by gravity, combining to form neutrons. What's left is a ball of neutrons held together by gravity and the neutron degeneracy pressure. Neutron degeneracy pressure is a quantum mechanical effect that prevents neutrons from occupying the same quantum state, creating pressure that resists further compression. A typical neutron star has about 1.4 solar masses compressed into a sphere only about 12 miles in diameter. That's about the size of a city, but with more mass than our entire sun. The density is mind-boggling. A sugar cube-sized piece of neutron star material would weigh about 100 million tons on Earth. That's roughly as much as all of humanity combined, squeezed into the size of a sugar cube. If you could somehow bring a teaspoon of neutron star material to Earth, it would weigh about 1 billion tons. That single teaspoon would weigh as much as nearly 900 Great Pyramids of Giza combined. The gravity on a neutron star's surface is about 100 billion times stronger than Earth's gravity. If you could stand on a neutron star, which you couldn't because you'd be instantly crushed to atomic thickness, you'd weigh billions of times more than you do on Earth. Neutron stars are extreme objects, but magnetars take that extremeness to another level. Magnetars are neutron stars, with magnetic fields about 1,000 times stronger than typical neutron stars. A typical neutron star might have a magnetic field of about 100 million Tesla. For comparison, Earth's magnetic field is about 50 microtesla, and the strongest continuous magnetic field ever created in a laboratory is about 45 Tesla. Neutron stars are already millions of times more magnetic than anything we can create. Magnetars have magnetic fields of about 100 billion Tesla. That's 100,000 trillion times stronger than Earth's magnetic field. These are the strongest magnetic fields known to exist in the universe. At these field strengths, strange things happen. Atoms become elongated into thin cylinders. The normal chemistry we're familiar with becomes impossible. Even empty space itself is affected. In quantum mechanics, empty space isn't truly empty. Virtual particles and antiparticles constantly pop into existence and annihilate each other. In the intense magnetic field of a magnetar, these virtual particles become real, creating a polarized vacuum that behaves almost like a solid material. Light passing through this region is affected. It becomes birefringent, meaning it splits into two beams with different polarizations, like light passing through certain crystals on Earth, but far more extreme. But here's where magnetars become terrifying. Magnetars are unstable. Their magnetic fields are so strong that they stress the neutron star's crust. Imagine the surface of the neutron star as a rigid crust of neutron-rich atomic nuclei floating on a fluid interior. The magnetic field lines thread through this crust. As the magnetic field evolves and shifts, it can build up tremendous stress in the crust. Eventually, the stress becomes too much and the crust cracks. This is called a starquake. When a magnetar's crust cracks, the magnetic field suddenly reconfigures, releasing enormous amounts of energy in a fraction of a second. This energy is released as a burst of X-rays and gamma rays. These events are called magnetar flares or giant flares. The largest magnetar flare ever observed occurred on December 27, 2004. A magnetar called SGR 1800 6-20, located about 50,000 light-years away on the opposite side of our galaxy, produced a giant flare. The initial burst lasted only 1/10 of a second, but in that tenth of a second, it released more energy than the Sun emits in 100,000 years. The gamma rays from this flare reached Earth and affected our planet's upper atmosphere. The ionosphere, the layer of atmosphere about 50 to 370 miles up that helps reflect radio signals, was measurably disturbed by the flare. Some satellites detected the radiation and went into safe mode. Radio communications were temporarily disrupted on the day side of Earth. This was from a flare that occurred 50,000 light-years away. The radiation had been traveling through space for 50,000 years before it reached us, and even after crossing that enormous distance, it was still powerful enough to affect Earth's atmosphere. Now imagine what would happen if a magnetar flare occurred much closer to us. If a magnetar within a few thousand light-years produced a giant flare, and Earth happened to be in the path of the radiation, the effects would be catastrophic. The gamma rays would strip away part of Earth's ozone layer within seconds. The ozone layer protects us from the sun's ultraviolet radiation. Without it, UV levels at the surface would increase dramatically. This would cause widespread sunburns and skin cancers in humans and animals. Plants would be damaged by the intense UV radiation, potentially leading to crop failures. Marine ecosystems would be particularly vulnerable because phytoplankton, the base of the ocean food chain, are sensitive to UV radiation. A large-scale die-off of phytoplankton could collapse ocean ecosystems and reduce the ocean's ability to absorb carbon dioxide from the atmosphere. The radiation from the flare would also create nitrogen oxides in the upper atmosphere. These nitrogen oxides would further deplete the ozone layer and create a brownish haze that could cool the planet, potentially triggering an ice age. Some scientists have suggested that past mass extinctions might have been caused by magnetar flares or other cosmic radiation events. There's no definitive proof. But the timing of some extinction events coincides with times when the solar system might have been passing through regions of the galaxy where magnetars are more common. The Ordovician extinction about 445 million years ago, which wiped out about 85% of marine species, is one candidate. So how many magnetars are there, and how worried should we be? Astronomers have identified about 30 magnetars in our galaxy. There are probably more that we haven't detected yet, perhaps a few hundred in total. Magnetars are rare, making up only about 10% of all neutron stars. Most neutron stars don't have strong enough magnetic fields to qualify as magnetars. Giant flares are also rare events. Each magnetar might produce a giant flare once every few thousand to tens of thousands of years. Given the number of magnetars in the galaxy and the frequency of giant flares, a dangerous flare happens somewhere in our galaxy every few 100,000 years on average. The chances of such a flare occurring close enough to Earth to be dangerous are very low in any given year. But over millions of years, it becomes more likely, and there's no way to predict when a magnetar will produce a flare. They don't follow a regular schedule. The flares seem to occur randomly, whenever the magnetic stresses in the crust build up to the breaking point. We can monitor known magnetars and watch for smaller flares that might indicate a giant flare is building, but we can't predict with certainty when or if a giant flare will occur. And here's something truly disturbing. Not all magnetars have been discovered yet. Magnetars are relatively faint objects unless they're producing a flare. Between flares, they're just dim X-ray sources that are hard to detect unless we're looking in the right direction with the right instruments. There could be a magnetar relatively close to Earth, within a few thousand light-years, that we simply haven't detected yet. It could have been quiet for decades or centuries, showing no signs of activity. And then one day, without warning, it could produce a giant flare. If Earth happened to be in the path of that radiation, we'd have no advance warning. The first indication would be the gamma rays hitting Earth's atmosphere. Within minutes, satellites would be affected. Within hours, the effects on the ozone layer would begin. Within days, UV radiation levels would spike. There's another aspect of magnetars that's deeply unsettling. Their magnetic fields are strong enough to be dangerous, even without a flare. If you could somehow get within 600 miles of a magnetar, which you can't because you'd be incinerated by radiation long before you got that close, the magnetic field would begin affecting the atoms in your body. At about 600 miles away, the magnetic field is strong enough to start distorting the electron clouds around atoms. Chemical bonds would start to break. The molecular structures that make up your cells would begin to fall apart. At a few hundred miles away, the magnetic field would be strong enough to rip apart the atoms themselves, tearing electrons away from nuclei. Your body would be torn apart at the atomic level, turned into a plasma of disconnected subatomic particles, and at just a few miles from the surface, the magnetic field would be strong enough to affect even the protons and neutrons inside atomic nuclei. The quarks that make up these particles would be stretched and distorted by the field. Matter as we know it simply cannot exist in such extreme magnetic environments. This makes magnetars uniquely terrifying among cosmic objects. Black holes will tear you apart with tidal forces, but at least the physics is familiar, just gravity stretched to its extreme. Magnetars create environments where the fundamental properties of matter change. They represent conditions so extreme that our normal understanding of chemistry and even atomic physics breaks down. The universe contains objects that are literally beyond our comprehension, places where the rules we're familiar with no longer apply. And these objects are real, scattered throughout our galaxy, occasionally producing bursts of radiation powerful enough to affect us across thousands of light-years of space. Now let's talk about something even more unsettling: vacuum decay. This is a theoretical possibility that comes from quantum field theory, the physics that describes the fundamental particles and forces of nature. And if it's real, it represents the ultimate cosmic threat, something that could destroy not just Earth or our solar system or even our galaxy, but the entire universe in an instant. Here's how it works. Everything in the universe exists in what physicists call quantum fields. There's an electromagnetic field that gives rise to light and electric forces. There are quark fields that give rise to the particles that make up protons and neutrons. There's a Higgs field that gives particles mass, and so on. Each of these fields exists everywhere in space at all times. Fields can exist in different energy states. The lowest energy state is called the true vacuum. It's the most stable configuration, the state the field naturally wants to be in. But fields can also exist in false vacuum states, higher energy configurations that are stable for a while, but not truly the lowest possible energy. Think of it like a ball sitting in a small valley on the side of a mountain. The ball is stable there. It won't roll away on its own, but it's not at the lowest possible elevation. There's a deeper valley at the base of the mountain. If something disturbs the ball, giving it enough energy to roll over the small ridge surrounding its current valley, it will roll down to the lower valley and release energy in the process. The current state of our universe might be like that ball. The Higgs field, which permeates all of space and gives fundamental particles their mass, might currently exist in a false vacuum state. It's stable, but not truly at the lowest possible energy configuration. If that's true, then it's theoretically possible for the Higgs field to undergo a transition to its true vacuum state. This transition wouldn't happen everywhere at once. It would start at a single point, perhaps triggered by a random quantum fluctuation or a high-energy particle collision. At that point, a bubble of true vacuum would form, expanding outward at the speed of light. Inside the bubble, the laws of physics would be different. The Higgs field would have a different value, which means particles would have different masses than they currently do. Electrons might be heavier or lighter. Quarks might have different masses, which would change the properties of protons and neutrons. The fundamental forces might have different strengths. These changes would be catastrophic for matter as we know it. Atoms would no longer be stable in the same way. Chemical bonds would break. Matter might not be able to form the same structures. Everything inside the bubble, every star, every planet, every living thing would be instantly destroyed, torn apart as the fundamental properties of matter changed. And the bubble would keep expanding at the speed of light. There would be no warning. Light itself travels at the speed of light, so the edge of the destruction would arrive at the same moment as any possible signal warning us of its approach. One moment, you'd be going about your day. The next moment, you and everything around you would cease to exist as the bubble of true vacuum swept past Earth. You wouldn't even have time to perceive what was happening. Your brain, your body, the ground beneath your feet, all of it would disintegrate in a fraction of a second as the very laws of physics holding matter together changed. And this process would continue until the entire observable universe was consumed. Every galaxy, every star, every planet, everything that exists would be destroyed and replaced with a new configuration of matter that operates under different physical laws. The old universe would be completely gone. These scenarios are called the Big Rip, and it represents an absolute end. Not just the end of humanity or life or Earth, but the end of everything. The entire universe replaced with something different, something that couldn't support stars or planets or life as we know it. To truly understand why vacuum decay is so terrifying, we need to go deeper into the physics. The Higgs field is one of several quantum fields that permeate all of space. When we say the Higgs field gives particles mass, what we mean is that particles interact with the Higgs field as they move through space. The strength of this interaction determines the particle's mass. Particles that interact strongly with the Higgs field have large masses. Particles that interact weakly have small masses. Photons don't interact with the Higgs field at all, which is why they have zero mass and travel at the speed of light. The Higgs field has a non-zero value everywhere in space, even in complete vacuum. This value is called the vacuum expectation value. It's essentially the field's baseline energy level. When physicists talk about the Higgs field being in a false vacuum state, they mean this baseline energy level might not be at its absolute minimum. Think of it like a ball balanced on a flat plateau on the side of a mountain. The ball is stable there. It won't roll away without being disturbed. But there's a lower elevation available, a valley at the base of the mountain. If the ball could somehow get past the edge of the plateau, it would roll down to the valley, releasing potential energy as it descended. The Higgs field's current state might be like that ball on the plateau. It's stable, but not at the true minimum energy. There could be a lower energy state available, the true vacuum, but there's an energy barrier preventing the field from transitioning to that state. Quantum mechanics, however, allows for a process called quantum tunneling. In quantum mechanics, particles and fields don't have to smoothly transition over energy barriers. They can tunnel through barriers probabilistically. It's as if the ball on the plateau could, through a quantum fluctuation, suddenly appear on the other side of the barrier and begin rolling down to the valley. For the Higgs field, this would mean a small region of space could spontaneously transition to the true vacuum state. This transition would create a bubble of true vacuum surrounded by false vacuum. The bubble would have a boundary, a wall where the field transitions from one state to another. This boundary would contain enormous amounts of energy. Think of it like surface tension in a water droplet. The surface of the droplet has energy associated with it because the water molecules at the surface are in a different environment than molecules in the interior. Similarly, the wall of a true vacuum bubble would have energy density far higher than anything we can create on Earth. Once the bubble forms, it expands. The expansion is driven by the energy difference between the true vacuum and the false vacuum. The false vacuum has higher energy, so it's energetically favorable for true vacuum to replace it. The bubble wall moves outward at nearly the speed of light. As it expands, the total energy in the wall increases because the surface area of the bubble is increasing. You might think this would slow down the expansion, but it doesn't. The energy comes from the conversion of false vacuum to true vacuum. Every bit of space that converts from false to true vacuum releases energy, and this energy goes into maintaining and accelerating the bubble wall. Inside the bubble, the laws of physics are different because the Higgs field has a different value. Let's think about what this means concretely. If the Higgs field's value changes, then the masses of fundamental particles change. Electrons might become heavier or lighter. Quarks, which make up protons and neutrons, might have different masses. The mass of a proton depends on the masses of its constituent quarks and on the binding energy holding them together. If quark masses change, proton masses change. If proton and neutron masses change substantially, atomic nuclei become unstable. The balance of forces holding nuclei together is delicate. The strong nuclear force binds protons and neutrons together. The electromagnetic force pushes protons apart because they're all positively charged. For stable nuclei, these forces balance. But if you change the masses of protons and neutrons, you change this balance. Nuclei that are currently stable might become unstable. They might spontaneously decay or fission into smaller pieces. Conversely, nuclei that are currently unstable might become stable. The entire table of elements could be completely different in the true vacuum. Elements that exist in our false vacuum universe might not exist in the true vacuum. New elements that don't exist here might be stable there. But here's the thing about atoms and chemistry. They depend very sensitively on the masses of particles. The size of an atom depends on the electron's mass and the strength of the electromagnetic force. The energy levels within an atom depend on these quantities. Chemical bonds form because electrons can be shared between atoms in ways that lower the total energy. If you change particle masses, you change everything about chemistry. Water might not form. Carbon might not form the complex molecules that make up living organisms. Stars might not be able to fuse hydrogen into helium because the nuclear reactions might have different energy requirements. The universe inside the true vacuum bubble would be a completely different place, governed by different physics, unable to support the structures we're familiar with. And this bubble is expanding at nearly the speed of light. Everything in its path is destroyed and converted. Stars are disrupted, planets disintegrate, galaxies are swept away. And because the bubble is moving at light speed, there's no escape. Nothing can outrun light. Even if a civilization detected the approaching bubble somehow, which they couldn't because the light carrying that information travels at the same speed as the bubble wall, they couldn't flee. Where would they go? The bubble is expanding in all directions. It's not coming from one direction that you could run away from. It's a spherical shell of destruction expanding from some point, growing larger and larger until it encompasses everything. And here's another disturbing thought. If our universe is in a false vacuum state, there could be multiple bubbles of true vacuum forming simultaneously in different locations. Each bubble would expand independently. Eventually, these bubbles would collide with each other. When two true vacuum bubbles collide, the collision releases tremendous amounts of energy. The bubble walls contain enormous energy density, and when they meet, that energy is released. This would create intense radiation and particles. But since everything inside the bubbles is already destroyed, there would be nothing to observe this collision except perhaps the quantum fields themselves reorganizing. Some theoretical physicists have speculated that our universe might have formed from a similar process, but in reverse. Perhaps our universe was originally in a true vacuum state, and a bubble of false vacuum formed and expanded. We're living inside that bubble of false vacuum. From this perspective, The ultimate fate of our universe would be a return to the true vacuum, completing the cycle. But this is purely speculative. We don't have enough understanding of quantum field theory and cosmology to say whether this is possible. There's one more disturbing aspect of vacuum decay to consider. The probability of vacuum decay might not be constant over time. It could be that the decay probability increases as the universe ages and evolves. Perhaps the conditions in the early universe made vacuum decay impossible or extremely unlikely. But as the universe expands and cools, as structures form and evolve, conditions might become more favorable for vacuum decay. Or perhaps high-energy processes increase the decay probability. Every time particles collide at high energies, there's a tiny chance that the collision could trigger a vacuum decay event. Cosmic rays colliding with Earth's atmosphere represent high-energy collisions. Particle accelerators like the Large Hadron Collider create even higher energy collisions, though still far below the energies needed to significantly increase decay probability, according to our current understanding. But what if we're wrong about those calculations? Before the Large Hadron Collider was built, some people raised concerns that it might create a black hole or trigger vacuum decay. Physicists calculated that the probability of such events was negligible, far lower than the probability of Earth being destroyed by a random meteor strike in the next second. The Large Hadron Collider has been operating for years now with no catastrophic events, which confirms those calculations were correct. But it illustrates that every new piece of technology that probes higher energies or creates more extreme conditions is, in principle, testing whether our understanding of vacuum stability is correct. So far, we've been right. But there's always a first time for being wrong. So, should we be worried about this? The honest answer is we don't know. Physicists have measured the properties of the Higgs field using particle accelerators like the Large Hadron Collider. Based on those measurements, we can calculate whether the Higgs field is in a true vacuum or a false vacuum. The results are troubling. According to our best measurements, the Higgs field appears to be in a false vacuum state, or at best, right on the boundary between false vacuum and true vacuum. This suggests that vacuum decay is at least theoretically possible. However, even if we're in a false vacuum, the transition to true vacuum might be incredibly unlikely. The energy barrier separating our current state from the true vacuum could be so high that a spontaneous transition would be fantastically improbable. We'd need a quantum fluctuation of enormous magnitude, or a particle collision at energies far beyond anything occurring naturally in the universe. Some calculations suggest that the universe could remain in its current false vacuum state for far longer than the current age of the universe, perhaps 10 to the power of 100 years or more. For context, the universe is currently 13.8 billion years old, which is about 10 to the power of 10 years. 10 to the power of 100 years is an incomprehensibly long time, far longer than the expected lifetime of stars or even black holes. So even if vacuum decay is possible, it might be so improbable that it will never happen during the lifetime of our universe. But might is doing a lot of work in that sentence. We don't know for certain. Our understanding of quantum field theory could be incomplete. There could be physics we don't understand yet that makes vacuum decay more or less likely than our current calculations suggest. What makes this especially unsettling is that vacuum decay could already be happening somewhere in the universe. A bubble of true vacuum could be expanding through distant space right now, billions of light years away, heading in our direction at the speed of light. We'd have no way to know until it arrived. That's the nature of an event moving at light speed. There's no warning, no way to detect it in advance. The universe could end tomorrow or in a trillion years, and we'd never know the difference until the moment it happened. Now let's turn to something that's not theoretical but absolutely real and happening right now all around us: cosmic rays. Cosmic rays are high-energy particles, mostly protons but also heavier atomic nuclei, traveling through space at speeds approaching the speed of light. They originate from various sources: supernova explosions, active galactic nuclei, colliding neutron stars, and potentially other exotic phenomena we don't fully understand. These particles carry enormous amounts of energy. The most energetic cosmic rays ever detected have energies around 50 joules. That might not sound like much. 50 joules is roughly the energy of a thrown baseball, but remember that energy is concentrated in a single subatomic particle. A proton is about 1.6 times 10 to the negative 27 kilograms, which is about 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 It must be traveling at almost exactly the speed of light. At that speed, relativistic effects become extreme. From the particle's perspective, time slows down dramatically due to time dilation. A cosmic ray traveling at 99.999999999%, the speed of light, experiences time passing more than 70 million times slower than we do. From the particle's perspective, crossing the entire Milky Way galaxy, a journey of 100,000 light-years, would take only about 45 days. These ultra-high energy cosmic rays are incredibly rare. Only about 1 particle per square kilometer per century reaches Earth's atmosphere at these extreme energies. But when they do, they create spectacular effects. When an ultra-high energy cosmic ray hits Earth's atmosphere, it collides with an atomic nucleus in the upper atmosphere, typically nitrogen or oxygen. The collision produces a cascade of secondary particles: pions, muons, electrons, and photons, each of which can collide with more atmospheric atoms, producing more particles. This creates an air shower, a cone of millions or even billions of particles spreading out from the initial collision point. The shower can be miles wide by the time it reaches the ground. Detectors on the ground can measure these showers and work backward to determine the energy and direction of the original cosmic ray. But let's understand exactly what makes cosmic rays so dangerous and so mysterious. Cosmic rays are misnamed. They're not rays at all. They're particles, mostly protons, but also heavier atomic nuclei and electrons. They were called rays when they were first discovered in 1912 by Victor Hess, who took electrometers up in balloons and discovered that radiation levels increased with altitude. He correctly concluded that this radiation was coming from space, not from Earth. At the time, physicists didn't know these were particles. They thought they might be some form of electromagnetic radiation, like X-rays, hence the name cosmic rays. The name stuck even after we learned they were actually particles. Most cosmic rays are protons, about 85%. About 12% are alpha particles, which are helium nuclei. The remaining 3% are heavier nuclei and electrons. These particles span an enormous range of energies. The lowest energy cosmic rays have energies comparable to thermal particles, just a few electron volts. These low-energy particles are abundant, but don't penetrate Earth's magnetosphere effectively. They're deflected by our magnetic field. Medium-energy cosmic rays have energies from millions to billions of electron volts. These can penetrate Earth's magnetosphere and atmosphere to varying degrees depending on their energy and where they strike. High-energy cosmic rays have energies from billions to trillions of electron volts. These are the ones that create air showers when they hit the atmosphere. And then there are the ultra-high-energy cosmic rays, with energies above about 10 to the 18th electron volts. These are the truly mind-boggling ones. The most energetic cosmic ray ever detected, observed in 1991, had an energy of about 3 times 10 to the 20th electron volts. This was a single subatomic particle carrying the same kinetic energy as a baseball thrown at about 60 miles per hour. That's about 50 joules of energy in a single proton. At that energy, the proton was traveling at more than 99.999999999999999999999999999% the speed of light. It was moving so close to light speed that if it raced a photon across the galaxy, it would arrive only about 1 second behind the photon, despite the journey taking 100,000 years. We call this particle the "oh my god" particle because that was apparently one physicist's reaction when they saw the data. And here's the mystery. We don't know what could accelerate a particle to such extreme energy. Most cosmic rays that reach Earth are relatively low energy, at least by cosmic standards. They're mostly deflected or absorbed by Earth's magnetic field and atmosphere. But the highest energy cosmic rays can punch through. The scary part isn't the ones we detect. It's what these particles tell us about the universe. The existence of ultra-high energy cosmic rays proves that somewhere in the universe, there are processes capable of accelerating particles to energies millions of times higher than anything we can achieve in our most powerful particle accelerators. The Large Hadron Collider, the most powerful accelerator ever built by humans, can accelerate protons to energies of about 13,000 billion electron volts, usually written as 13 tera-electron volts or 13 TeV. That's already an incredible achievement, requiring a circular tunnel about 17 miles in circumference and superconducting magnets operating at near absolute zero temperature. But the highest energy cosmic rays have energies around 300 million TeV, or 300 exa-electron volts. That's roughly 20 million times more energetic than anything the Large Hadron Collider can produce. We don't fully understand what natural processes can generate such extreme energies. Supernova explosions can accelerate particles, but not to these ultra-high energies. Active galactic nuclei, regions around supermassive black holes where matter is falling inward and releasing tremendous amounts of energy, are a likely source. The powerful magnetic fields and intense radiation near these black holes could potentially accelerate particles to extreme speeds. But we're not certain. What's terrifying is that these particles exist, and they're traveling through space constantly. Earth is being bombarded by cosmic rays every second of every day. Most are harmless, absorbed by the atmosphere long before they reach the surface. But over geological time, cosmic rays have measurable effects. Cosmic rays cause mutations in DNA. Most mutations are harmless or lethal to the cell, but occasionally a mutation gives an organism a beneficial trait. Over millions of years, cosmic ray-induced mutations contribute to evolution. You exist partly because cosmic rays have been mutating the DNA of your ancestors for billions of years. Cosmic rays can also affect electronics. A high-energy particle striking a computer chip can flip a bit, changing a 0 to a 1, or vice versa. In most cases, this causes a minor glitch that goes unnoticed. But in critical systems like airplane control, computers, or medical devices, or nuclear reactor controls, a single bit flip could potentially cause a malfunction with serious consequences. Engineers design important systems with redundancy and error correction to prevent this, but it remains a concern. There have been documented cases of cosmic rays causing problems. In 2003, a cosmic ray struck a voting machine in Belgium during an election, flipping a bit that added 4,096 extra votes to one candidate's total. The error was caught during vote verification, but it demonstrates that cosmic rays can have real-world effects. In 2008, a cosmic ray struck a computer controlling a commercial aircraft in flight over Australia, causing the autopilot to malfunction and send the plane into a sudden dive. Passengers were thrown against the ceiling, dozens were injured, and the pilots had to take manual control to save the plane. Investigation traced the malfunction to a single-bit flip in the flight computer's memory, most likely caused by a cosmic ray. These incidents are rare, but they highlight an uncomfortable truth. We're living in a radiation environment that we can't fully control or predict. Invisible particles are constantly passing through your body right now. Several cosmic rays likely passed through you while you were reading this sentence. Most do no harm, but occasionally one will strike a DNA molecule in a cell, causing a mutation. Usually, the cell's repair mechanisms fix the damage. Sometimes, the cell dies. And very rarely, the mutation causes the cell to become cancerous. Scientists estimate that cosmic rays are responsible for a small but measurable fraction of cancer cases, perhaps 1 or 2%. That might not sound like much, but it means tens of thousands of people die every year from cancers caused by particles that traveled across the galaxy to strike them at exactly the wrong place, at the wrong time, and there's nothing we can do about it. We can't shield ourselves from cosmic rays, at least not without surrounding ourselves with meters of rock or water, which is impractical for daily life. Earth's atmosphere and magnetic field provide some protection, but not complete protection. If we ever establish colonies on other worlds like Mars or the Moon, which lack Earth's thick atmosphere and strong magnetic field, cosmic ray exposure will be a serious health concern. Astronauts on long-duration space missions are exposed to much higher levels of cosmic radiation than people on Earth. A trip to Mars would expose astronauts to radiation levels many times higher than the annual exposure limits set for nuclear workers on Earth. This increases their risk of cancer and other radiation-related health problems. And we can't shield spacecraft effectively against cosmic rays without making them prohibitively heavy. We're stuck with this danger as long as we venture into space. Let's talk about something happening much closer to home: solar storms. Our sun is not a stable, constant source of light and heat. It's a churning ball of plasma with a complex magnetic field that regularly produces violent outbursts. The sun goes through an 11-year cycle of activity. During solar maximum, the peak of the cycle, the sun produces frequent solar flares and coronal mass ejections. Solar flares are sudden, intense bursts of radiation, mostly X-rays and ultraviolet light. Coronal mass ejections, or CMEs, are massive eruptions of plasma and magnetic field from the sun's outer atmosphere. A large CME can eject billions of tons of plasma into space at speeds of several million miles per hour. When a CME is directed toward Earth, it takes about 1 to 3 days for the ejected plasma to cross the distance between the Sun and Earth. When it arrives, it compresses Earth's magnetosphere, the magnetic field surrounding our planet. This interaction produces beautiful auroras, the northern and southern lights, as charged particles from the Sun follow Earth's magnetic field lines down toward the poles and collide with atoms in the upper atmosphere. But CMEs can also cause serious problems. The changing magnetic field induces electric currents in long conductors on Earth's surface, like power lines. These induced currents can overload transformers, causing them to overheat and fail. In 1989, a moderate solar storm caused a power blackout across Quebec, Canada. 6 million people lost electricity for 9 hours because the storm damaged transformers in the power grid. But that was a relatively minor event compared to what the sun is capable of producing. In 1859, a massive solar storm called the Carrington Event struck Earth. It's named after Richard Carrington, an amateur astronomer who happened to be observing the sun when the flare erupted. He saw a bright flash of white light on the sun's surface, lasting only a few minutes. That flash was visible to the naked eye through his telescope, which should give you a sense of how powerful the flare was. About 17 hours later, the associated CME hit Earth. The impact was dramatic. Auroras were visible as far south as the Caribbean and Hawaii. Telegraph systems worldwide went haywire. Some telegraph operators reported receiving electric shocks from their equipment. In some cases, telegraph wires sparked and caught fire. Some telegraph systems continued operating even after their batteries were disconnected, powered solely by the currents induced by the storm. In 1859, society wasn't heavily dependent on electrical systems. Telegraphs were affected, but that was about it. Life went on. Today, a Carrington-level event would be catastrophic. Our modern civilization depends on electricity for almost everything: power generation and distribution, water treatment and pumping, sewage systems, communications, transportation, banking, food distribution, medical equipment. Everything relies on functioning electrical infrastructure. A severe solar storm could damage transformers across entire continents. Transformers are custom-built, expensive, and take months or years to manufacture and install. If hundreds or thousands of transformers were damaged simultaneously, we wouldn't have enough replacement units available. Power could be out for months or years in some regions. Without electricity, water systems fail, sewage treatment stops, food spoils, hospitals can't function, communications collapse. In today's interconnected world, a long-duration power outage across a large region would lead to social breakdown. Governments would struggle to maintain order. Supply chains would collapse. People would lack access to food, clean water, and medical care. The death toll could be in the millions. Studies by government agencies and international organizations have estimated that a Carrington-level event today could cause economic damage in the trillions of dollars and set civilization back decades in affected regions. How likely is such an event? The Carrington event happened in 1859. We've had other severe solar storms since then, none quite as powerful. In 2012, a CME comparable to the Carrington event erupted from the Sun, but fortunately, it was directed away from Earth. If it had happened 1 week earlier, when Earth was in that part of its orbit, it would have hit us directly. Scientists studying the 2012 event concluded that it would have caused widespread damage to power grids and satellites if it had struck Earth. We got lucky. The Sun produces Carrington-level storms roughly once per century on average, based on historical records and ice core data. That means we're overdue. It's been more than 160 years since the Carrington event. Statistically, we could experience another one at any time. And unlike asteroid impacts or rogue black holes, we know solar storms happen regularly. It's not a matter of if, but when. Space agencies and governments are aware of this threat. Satellites monitor the Sun constantly, watching for flares and CMEs. When a CME is detected heading toward Earth, warnings are issued to power companies, satellite operators, and airlines. Power companies can take steps to protect transformers, disconnecting vulnerable equipment or reducing load. Satellite operators can put satellites into safe mode to minimize damage. Airlines can reroute flights to avoid polar regions where radiation exposure is highest during storms. But these measures only provide partial protection. A truly massive storm might overwhelm our defenses, and there's no way to prevent a solar storm from happening. All we can do is try to prepare and hope the next big one isn't too severe. Let's dive deeper into what actually happens during a severe solar storm and why our modern infrastructure is so vulnerable. Our Sun is essentially a gigantic ball of plasma, hydrogen and helium heated to millions of degrees. This plasma is electrically charged, and moving charges create magnetic fields. The Sun's rotation and the convection of plasma within it create complex, tangled magnetic field lines. Sometimes these magnetic field lines become so twisted and stressed that they snap, releasing enormous amounts of energy in an instant. This is a solar flare. Solar flares release energy across the electromagnetic spectrum, from radio waves to gamma rays. The most intense flares, classified as X-class flares, release energy equivalent to millions of nuclear bombs. But flares themselves don't directly threaten Earth's power grid. The electromagnetic radiation from a flare travels at the speed of light and reaches Earth in about 8 minutes. This radiation can affect radio communications and satellite operations, but it doesn't significantly impact ground-based infrastructure. What's dangerous is the coronal mass ejection that often accompanies a flare. A CME is a massive eruption of plasma from the Sun's corona, its outer atmosphere. Unlike the radiation from a flare, a CME contains actual matter, charged particles that travel through space at speeds typically between 250 and 1,250 miles per second. That's fast, but it's much slower than light, which travels at about 186,000 miles per second. So, a CME takes anywhere from about 15 hours to several days to reach Earth, depending on its speed. When the CME's magnetic field impacts Earth's magnetic field, interesting things happen. Earth's magnetic field is our first line of defense against charged particles from space. The field extends about 37,000 miles on the sunward side and trails out behind Earth for hundreds of thousands of miles on the night side. This magnetic bubble, called the magnetosphere, normally deflects most of the charged particles from the Sun, channeling them around Earth. But a CME can compress and distort the magnetosphere dramatically. The CME carries its own magnetic field with it. When this field collides with Earth's field, they can reconnect in a process called magnetic reconnection. Imagine two magnetic field lines from different sources touching. The field lines can break and rejoin in new configurations, releasing energy in the process. This reconnection allows some of the CME's energy and particles to penetrate deeper into the magnetosphere than normal. The particles spiral along Earth's magnetic field lines, following them down toward the poles. When these particles collide with atoms and molecules in Earth's upper atmosphere, they excite those atoms, causing them to emit light. This is what creates the auroras, the northern and southern lights. During a severe storm, so many particles pour into the atmosphere that auroras become visible at much lower latitudes than usual. During the Carrington event, auroras were seen as far south as Cuba and Hawaii. People in the northeastern United States could read newspapers by the light of the aurora at midnight. Imagine looking up at the sky and seeing curtains of green, red, and purple light rippling across the heavens, bright enough to cast shadows. It would be beautiful and terrifying at the same time. But the auroras are just a visible symptom of what's happening. The real danger comes from the changing magnetic field. As the magnetosphere is compressed and then rebounds, as magnetic field lines reconnect and reconfigure, Earth's magnetic field changes rapidly. These rapid changes in the magnetic field induce electric currents in any long conductor. This is Faraday's law of electromagnetic induction, a fundamental principle of physics. A changing magnetic field creates an electric field, and that electric field drives currents through conductors. Power lines stretching across the landscape are perfect long conductors for induced currents. The longer the conductor, the more current is induced. Power grids in high-latitude regions like Canada, Scandinavia, and Russia are particularly vulnerable because they're closer to the poles where the magnetic field effects are strongest. But even mid-latitude grids can be affected by severe storms. When these geomagnetically induced currents, or GICs, flow into power transformers, bad things happen. Transformers are designed to handle alternating current at specific frequencies, typically 50 or 60 cycles per second depending on the country. GICs are essentially direct current or extremely low-frequency alternating current. Transformers aren't designed to handle DC or very low-frequency AC. When GICs flow through a transformer, they can saturate the transformer's core. The magnetic core inside the transformer becomes fully magnetized and can't respond properly to the normal alternating current. This causes the transformer to overheat. The transformer might draw more current from the grid, creating additional load. Hot spots can develop in the windings. If the current is strong enough and lasts long enough, the transformer can overheat to the point of permanent damage. The insulation inside the transformer can degrade or melt. In extreme cases, the transformer can catch fire or explode. And here's the critical problem. Large power transformers are custom-built for specific locations. They weigh hundreds of tons and cost millions of dollars each. Manufacturing one takes months or even years. There's no warehouse full of spare transformers sitting around waiting to be installed. When a transformer is damaged, it has to be replaced, and that takes time. If a severe solar storm damages hundreds of transformers across a continent simultaneously, we simply don't have enough replacement capacity. Power could be out for months or years in some regions, while new transformers are manufactured and installed. Now, think about what that means for modern society. Without electricity, water treatment plants stop functioning. Water pumps stop working. In a matter of days, people in cities would have no access to clean water. Sewage treatment would halt, leading to sanitation crises. Hospitals rely on electricity for everything from lighting to life support equipment to refrigeration for medicines. They have backup generators, but those generators need fuel, and fuel distribution depends on electricity and communications. Communications networks would collapse. Cell towers have backup batteries, but those typically last only a few hours. Internet infrastructure requires power. Landline phones might work for a while, but eventually, those networks would fail too. Banking systems would be offline, making it impossible to access money electronically. ATMs wouldn't work. Credit and debit cards would be useless. Grocery stores depend on daily or even multiple daily deliveries of food. Their shelves empty quickly under normal circumstances. In a prolonged blackout, food distribution would collapse within days. Gas stations need electricity to pump fuel, so transportation would grind to a halt. Emergency services would be overwhelmed. Police, fire, and medical services rely on communications and transportation, both of which would be severely disrupted. Maintaining order would become difficult. In the past, societies were more resilient to loss of electricity because they didn't depend on it as much. In 1859, when the Carrington event occurred, electricity was a novelty. Telegraph systems were affected, but life went on. Today, we're completely dependent on continuous electricity supply. A long-term, widespread blackout would be a catastrophe of unprecedented scale. Government agencies have conducted studies of this scenario. A 2008 report by the National Research Council estimated that a severe geomagnetic storm could leave 20 to 40 million people without power for months, 2 years, cause economic damages exceeding $2 trillion, and require 4 to 10 years for full recovery. That's for a single country, the United States. A global event affecting multiple countries simultaneously would be even worse. International cooperation would be difficult if all affected countries are dealing with their own crises simultaneously. Some countries are taking steps to harden their power grids against geomagnetic storms. Utilities can install blocking devices that prevent GICs from entering transformers. They can design grids with more redundancy. They can stockpile critical spare parts. But these measures are expensive, and not all countries or utilities are implementing them. The question is whether we'll have adequate protection in place before the next major storm hits. And we know another major storm is coming, eventually. The sun goes through its 11-year cycle, But even within that cycle, there's variability. Some solar maxima are more active than others. Solar cycle 24, which peaked around 2012 to 2014, was actually quite weak. Solar cycle 25, which began in December 2019, is expected to peak around 2025. Early indications suggest it might be more active than the previous cycle. Every solar cycle increases the probability of a major CME directed at Earth, and eventually, our luck will run out. It's not a question of if, but when. The best we can do is improve our monitoring, improve our predictions, and improve our defenses. We need better satellites observing the sun. We need better models predicting CME trajectories and arrival times. We need hardened infrastructure that can withstand induced currents. We need backup systems and emergency plans. But even with all that, a truly massive storm, larger than the Carrington event, might overwhelm our defenses. The Sun is capable of producing CMEs even larger than what we saw in 1859 or 2012. We know this from studying other Sun-like stars and from examining ice cores and tree rings that preserve records of past solar activity. Some evidence suggests that superflares, events 10 or even 100 times more powerful than the Carrington event, occur on Sun-like stars rarely but regularly. If our Sun produced a superflare, the consequences would be civilization ending. Not extinction level, humans would survive, but civilization as we know it might not. We'd be thrown back technologically, perhaps to pre-industrial levels, for a generation or more. And the most frightening part is that this could happen tomorrow, or next week, or next year. We wouldn't know until the CME was already on its way, giving us at most a few days' warning. Let's shift to something even more exotic and disturbing. Fast radio bursts. Fast radio bursts, or FRBs, are brief, intense pulses of radio waves coming from deep space. Each burst lasts only a few milliseconds, but in that short time it releases as much energy as the Sun emits in several days. The first FRB was discovered in 2007 by astronomers analyzing old data from a radio telescope. Since then, hundreds more have been detected. They occur randomly across the sky, with no obvious pattern. Most FRBs are one-time events, appearing once and never repeating. A few have been observed to repeat, producing multiple bursts from the same location over months or years. Here's what makes FRBs unsettling. We don't know what causes them. The energy released in a fast radio burst is enormous. To produce that much energy in such a short time requires something extreme. Astronomers have proposed various explanations. Magnetars, neutron stars with incredibly powerful magnetic fields, could produce FRBs through some kind of magnetic eruption or starquake. Colliding neutron stars might produce FRBs during the final moments before they merge. Evaporating black holes, if they exist, might emit FRBs as they disappear in a final burst of Hawking radiation. Some scientists have even suggested that FRBs could be artificially produced by advanced alien civilizations, perhaps as beacons or as propulsion systems for spacecraft. We simply don't know. All the explanations are speculative. The distances involved are huge. Most detected FRBs originated billions of light-years away. The radio waves have been traveling across the universe for billions of years before reaching Earth. This means the events producing FRBs were incredibly powerful. You can see a candle flame from a few miles away under dark conditions. To be visible from billions of light-years away, an event would need to be billions of times brighter than that candle. FRBs are that bright, but only in radio wavelengths, and only for a few milliseconds. What's disturbing is that these intense bursts of energy are occurring throughout the universe, constantly. Astronomers estimate that thousands of FRBs occur every day across the entire sky. We only detect a small fraction of them because our radio telescopes can't monitor the whole sky simultaneously, and because many FRBs are too faint or too brief to detect, even when we're looking in the right direction. But they're out there, mysterious, powerful events happening all the time for reasons we don't understand. Some scientists have speculated, though it's highly uncertain, that if an FRB occurred close enough to Earth, it could be dangerous. The radio energy would be intense enough to potentially disrupt electronics or even cause biological damage. But how close is close enough? Nobody knows. The nearest FRB detected so far was about 500 million light-years away. No FRBs have been detected from within our own galaxy, the Milky Way. If one occurred within a few thousand light-years of Earth, the received signal would be millions of times stronger than the FRBs we've detected from distant galaxies. Would that be dangerous? It might depend on the exact nature of the burst. Radio waves at normal intensities are harmless. They pass through your body constantly from radio stations, cell towers, Wi-Fi routers, and cosmic sources, and cause no harm. But an extremely intense pulse of radio energy could potentially have effects. It might induce electrical currents in long conductors, similar to a solar storm, but potentially more intense and more localized. It might damage satellites or radio telescopes directly exposed to the burst. Whether it would harm biological tissue is uncertain. Probably not, unless the intensity was extreme beyond anything we've observed. But here's the unsettling part. We don't know what produces FRBs. We don't know how often they occur in our galaxy. We don't know if they're increasing or decreasing in frequency. We don't know if there are different types of FRBs with different properties. We're detecting mysterious, powerful events occurring throughout the universe, and we have no idea what's causing them. That uncertainty is disturbing. We like to think we understand the universe, that we've figured out the basic rules, and it's just a matter of filling in details. FRBs remind us that there are still big mysteries out there, phenomena we can't explain with our current theories. And if we don't understand what's causing them, we can't predict if or when they might pose a danger. Now, let's discuss something that sounds like it belongs in a horror movie, but is real and observed. Cannibal galaxies. Galaxies consuming other galaxies. The Milky Way, our home galaxy, is a cannibal. It's currently in the process of devouring several smaller galaxies. The Sagittarius Dwarf Elliptical Galaxy is one victim. This small galaxy, containing about 10 million stars, is being torn apart by the Milky Way's gravity. Long streams of stars pulled from Sagittarius loop around the Milky Way, gradually being absorbed into our galaxy's structure. The Canis Major Dwarf Galaxy is another victim, also being ripped apart and consumed. This process is called galactic cannibalism, or hierarchical galaxy formation. It's how large galaxies grow over time. Small galaxies merge or are absorbed by larger ones, which in turn merge with other large galaxies. Computer simulations show that most large galaxies like the Milky Way have grown through countless mergers over billions of years. The Milky Way has consumed dozens, possibly hundreds of smaller galaxies throughout its history. Each time, the smaller galaxies' stars are scattered and mixed into the Milky Way's structure. The small galaxy ceases to exist as a separate entity, its identity erased as its stars become part of the larger galaxy. In a few billion years, the Milky Way will undergo its most dramatic merger yet. The Andromeda Galaxy, the nearest large galaxy to us, is heading in our direction. Andromeda is about 2.5 million light-years away right now, but it's approaching at roughly 68 miles per second. That might not sound fast compared to the speed of light, but over billions of years, it adds up. In about 4 billion years, Andromeda and the Milky Way will collide. This won't be a collision in the usual sense. Galaxies are mostly empty space. The distances between stars are so vast that even when two galaxies merge, individual stars almost never collide. But the gravitational interactions will be dramatic. As the two galaxies approach, their shapes will distort. Long tidal tails of stars will be pulled from each galaxy, stretching out into space. The spiral structures of both galaxies will be disrupted, their elegant arms torn apart by tidal forces. When the galaxies first pass through each other, the stars will intermingle but then separate again as each galaxy's momentum carries it past the other. But gravity will pull them back together. They'll swing around and pass through each other again and again, each passage further mixing their stars and disrupting their structures. Over billions of years, the two galaxies will eventually merge completely, forming a single elliptical galaxy. All the stars from both galaxies will be jumbled together in a featureless elliptical blob, no more spiral arms, no more distinct structures, just a cloud of stars in chaotic orbits. Astronomers have already observed many galaxy mergers in progress throughout the universe. Some galaxies show clear signs of recent mergers, distorted shapes, long tidal tails, and double galactic nuclei, where two supermassive black holes from the merged galaxies haven't yet combined. These observations, combined with computer simulations, give us confidence that we understand what will happen when Andromeda and the Milky Way merge. For humanity, if we still exist in 4 billion years, this merger will be spectacular to watch but not immediately dangerous. As mentioned, stars won't collide. The sun will pass through the chaos, with plenty of space around it. But the gravitational chaos might disturb the Oort cloud, sending comets plunging into the inner solar system, bombarding Earth over millions of years. Additionally, our sun's orbit around the galactic center will be disrupted. Currently, the sun orbits about 26,000 light-years from the Milky Way's center, in a relatively safe region between spiral arms. After the merger, the sun might end up in a different orbit, potentially closer to the new galaxy's center, where conditions are more chaotic and radiation levels are higher. Or the sun might be flung outward to the outer regions of the new galaxy, far from the galactic core. Earth's fate during the merger depends on many unpredictable factors. We might get through it relatively unscathed, or we might face catastrophic comet bombardment, or Earth might be ejected from the solar system by a close encounter with a passing star, or any number of other possibilities. But here's the truly unsettling realization. This process of galaxies consuming each other is happening all over the universe, constantly. At any given moment, thousands of galaxy mergers are in progress. The universe is not a peaceful place where galaxies drift serenely through space. It's a violent place where gravitational forces tear structures apart and build new ones from the wreckage. And this violence operates on timescales so long that we perceive it as stillness. 4 billion years is an incomprehensibly long time from a human perspective. Civilizations rise and fall in thousands of years. Species evolve over millions of years. Continents drift over tens of millions of years. But galaxies collide over billions of years. To the universe, this is normal, routine. But from our perspective, it's terrifying to realize that our entire galaxy is doomed. Not in some distant heat death of the universe scenario, but in a violent collision that will scramble everything we know. All the constellations, all the familiar stars, everything will be mixed up and scattered. The Milky Way as a distinct entity will cease to exist. Let's turn our attention to something happening right now that most people don't know about. The universe is expanding, and that expansion is accelerating. This was discovered in 1998 by two teams of astronomers studying distant supernovae. They expected to measure how much the universe's expansion was slowing down over time. Gravity should be pulling everything back together, gradually slowing the expansion that began with the Big Bang. That's what everyone assumed, but the observations showed the opposite. The expansion isn't slowing down, it's speeding up. Distant galaxies are receding from us faster than they should be, based on gravity alone. Something is pushing the universe apart, counteracting gravity and causing the expansion to accelerate. Astronomers call this mysterious, something dark energy. We don't know what dark energy is. It's not matter or radiation or anything we can directly detect. It's a property of space itself, a kind of inherent energy that causes space to expand. The more space there is, the more dark energy there is, which pushes space to expand even faster, creating more space and more dark energy in a runaway process. Currently, dark energy makes up about 68% of all the energy in the universe. Dark matter, another mysterious substance we don't understand, makes up about 27%. Normal matter, the stuff that makes up stars and planets, and you, is only about 5% of the total. We live in a universe where 95% of its content is something we don't understand. That's humbling and disturbing. But here's why dark energy is terrifying. If the expansion continues accelerating, the universe will eventually be torn apart. This scenario is called the Big Rip. Here's how it works. Right now, dark energy is relatively weak. It causes expansion on the largest scales, but it's not strong enough to overcome the gravity holding galaxies together, or solar systems together, or atoms together. But if dark energy continues to strengthen over time, which some theoretical models predict, it will eventually become strong enough to overcome all other forces. First, galaxy clusters will be pulled apart. Galaxies that are currently bound together by gravity will be pulled apart as space between them expands faster than gravity can hold them together. Then individual galaxies will be torn apart. The Milky Way would be ripped to pieces. Stars scattered as space expands too quickly for gravity to hold the galaxy together. Then solar systems would be torn apart. Planets would be flung away from their stars as the space between them expands faster than gravity can maintain orbits. Eventually, stars themselves would be torn apart. The gravity holding a star together would be overcome by the expansion of space within the star. Then planets would be torn apart. Rocks and mountains and structures would all disintegrate as space expands too rapidly for molecular bonds to hold them together. Then molecules would be torn apart, then atoms, then atomic nuclei. In the final moments before the Big Rip, space would expand so rapidly that individual particles would be ripped apart, torn down to whatever fundamental components exist beneath quarks and electrons. The entire universe would be reduced to a dispersed soup of fundamental particles, unable to interact because space itself is expanding too quickly. This is the Big Rip, and it represents an absolute end to everything. When would this happen? Current estimates, based on measurements of dark energy's properties, suggest the Big Rip might occur in about 22 billion years. But there's enormous uncertainty in that number. It depends on the exact nature of dark energy, which we don't understand. Some models of dark energy predict that it will remain constant or even weaken over time, in which case the Big Rip would never occur. Other models predict that dark energy will strengthen, leading to the Big Rip sooner rather than later. We don't know which model is correct because we don't know what dark energy is. Here's what's deeply unsettling about this. We discovered dark energy by accident while studying distant supernovae. We weren't looking for it, we didn't predict it, and we still don't understand it. But it's the dominant component of the universe, determining the ultimate fate of everything that exists. And we have no idea how it works or what will happen next. It's possible that dark energy will remain constant, and the universe will expand forever but gently. Stars gradually burning out as galaxies drift apart, but no catastrophic ripping. It's possible that dark energy will weaken and expansion will slow, maybe even reverse, leading to a big crunch where the universe collapses back on itself, or dark energy could strengthen and tear everything apart in the Big Rip. We can't predict which scenario will occur because we lack the fundamental understanding of what we're dealing with. This uncertainty about the fate of the entire universe is profoundly disturbing. We like to think science gives us answers, that we understand how things work and can predict what will happen. But when it comes to the ultimate fate of the universe, we're still guessing. We're like passengers on a train, with no idea where the train is going or whether there are tracks ahead. Finally, let's discuss something that's both fascinating and terrifying in equal measure: the Great Filter. The Great Filter is a concept from the Fermi paradox, the question of why we haven't detected any signs of alien civilizations despite the vast number of potentially habitable planets in the universe. The paradox goes like this: the universe is huge, containing trillions of galaxies, each with hundreds of billions of stars. Many of those stars have planets, and many of those planets are in the habitable zone where liquid water could exist. The universe is also old, 13.8 billion years. That's plenty of time for life to arise and evolve on other worlds. If life is common, and if intelligent life occasionally evolves, then the universe should be teeming with civilizations. Some of those civilizations should be far older and more advanced than us, potentially millions or even billions of years ahead. Advanced civilizations should be able to colonize their home star system, then expand to other star systems, gradually spreading across the galaxy. Even traveling at modest speeds far below the speed of light, a civilization could colonize the entire galaxy in a few million years, which is a blink of an eye on cosmic timescales. If civilizations commonly arise and expand, then our galaxy should already be colonized. We should see evidence of alien technology everywhere: megastructures around stars, radio signals, spacecraft, probes visiting our solar system, but we see nothing. The galaxy appears empty. No signals, no spacecraft, no obvious signs of intelligence anywhere we look. This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked, "Where is everybody?" One proposed solution to the paradox is the Great Filter. The Great Filter is a hypothetical barrier that prevents most life from reaching the stage where it can expand across the galaxy. Maybe life is common, but intelligent life is rare. Maybe intelligence is common, but technology is rare. Maybe technology is common, but interstellar travel is impossible or impractical. Or maybe civilizations commonly destroy themselves before they can expand beyond their home planet. The Great Filter could be behind us or ahead of us, and that's where the terror comes in. If the Great Filter is behind us, then we're incredibly lucky. We've already passed the most difficult challenges, the steps that prevent most life from becoming a spacefaring civilization. Maybe the origin of life is incredibly rare, and Earth is one of the few places where it happened. Maybe the evolution of complex multicellular life is incredibly unlikely. Maybe intelligence rarely evolves. If the Great Filter is behind us, then we're unique or nearly unique, and we have a good chance of surviving and eventually colonizing the galaxy. That's the optimistic interpretation. But if the Great Filter is ahead of us, then we're in serious trouble. It means something terrible happens to most civilizations at or near our current level of development. Something that prevents them from expanding beyond their home world. Maybe all civilizations eventually destroy themselves through war or environmental catastrophe. Maybe they develop technologies that inevitably lead to extinction. Maybe there's some cosmic threat that wipes out civilizations when they reach a certain level of technology. We don't know, and that's what makes it terrifying. If the Great Filter is ahead of us, then the silence of the universe takes on a sinister meaning. The universe is quiet, not because intelligence is rare, but because intelligent civilizations don't last long. They rise, they develop technology, and then something happens that destroys them before they can spread. And we're approaching that same fate. What could the great filter be if it's ahead of us? Some possibilities are depressingly plausible. Nuclear war. We've had nuclear weapons for less than 80 years, and we've already come close to nuclear war multiple times. The Cuban Missile Crisis in 1962 brought the US and Soviet Union to the brink of nuclear war. Several other incidents involving false alarms or miscommunications could have triggered nuclear exchanges. We've been lucky so far, but will our luck hold? As nuclear weapons proliferate to more countries, the risk increases. Eventually, a nuclear war might occur, killing billions and potentially rendering Earth uninhabitable. Climate change. We're currently warming Earth's climate by burning fossil fuels and releasing greenhouse gases. If we can't control this warming, it could trigger runaway feedback loops. Melting permafrost could release huge amounts of methane, a powerful greenhouse gas, accelerating warming. Melting ice caps would reduce Earth's reflectivity, causing more solar energy to be absorbed, accelerating warming further. Oceans could become acidic, killing marine ecosystems. Agriculture could fail as weather patterns shift. In a worst-case scenario, Earth could become uninhabitable for most life, including humans. Artificial intelligence. We're rapidly developing more advanced AI systems. If we create artificial general intelligence, AI that can match or exceed human intelligence across all domains, we might lose control. An advanced AI might pursue goals that are incompatible with human survival. It might see humans as threats to be eliminated or as resources to be used. If AI develops too quickly, before we've figured out how to align its goals with ours, it could lead to human extinction. Synthetic biology or nanotechnology. As our biotechnology advances, we're gaining the ability to engineer viruses and bacteria. A designed pathogen, whether created intentionally as a weapon or accidentally released from a lab, could potentially wipe out humanity. Similarly, advanced nanotechnology could allow the creation of self-replicating machines. If such machines were poorly designed or malicious, they could consume all organic matter on Earth, turning the biosphere into grey goo. These scenarios sound like science fiction, but they're all plausible outcomes of technologies we're currently developing or will develop in the near future. If the great filter is ahead of us, one of these or something similar might be our fate. And here's the truly disturbing part. If we eventually detect signs of alien life, particularly complex or intelligent life, that would be bad news for us. Finding alien civilizations would mean the great filter isn't that unusual for life to arise and develop intelligence, which means the great filter is probably ahead of us. It's something that happens to advanced civilizations. The more common intelligent life turns out to be, the more likely it is that we're doomed. The silence of the universe might actually be our best hope. If we're alone or nearly alone, it suggests the great filter is behind us. The hard steps were becoming life, becoming complex, becoming intelligent. We've already beat the odds. But if the universe is teeming with life, then the silence means something terrible happens to most civilizations, and we're likely to suffer the same fate. So every time astronomers search for signs of alien life and find nothing, there's a strange relief mixed with disappointment. We want to find alien life to know we're not alone. But finding it might confirm that we're approaching a filter that will destroy us. Let's explore this concept more deeply, because it has profound implications for humanity's future and our place in the universe. The Fermi paradox begins with some basic assumptions and observations. First, the universe is old, 13.8 billion years old. Our galaxy formed about 13 billion years ago. Earth formed 4.6 billion years ago, That means there were 8 to 9 billion years of cosmic history before Earth even existed. Stars were forming, living, dying, and creating heavy elements. Planetary systems were forming around those stars. Second, the universe is huge. The observable universe contains about 2 trillion galaxies. Our galaxy alone contains between 100 and 400 billion stars. Recent observations suggest that most stars have planets, at least 1 planet per star on average, possibly more. That means there are trillions of planets in our galaxy alone. Third, many of these planets are in the habitable zone, the range of distances from their star where liquid water can exist on the surface. Estimates vary, but there might be billions of potentially habitable planets in our galaxy. Fourth, life arose on Earth relatively quickly. Earth formed about 4.6 billion years ago. The oldest evidence of life dates to about 3.8 billion years ago. That's only about 800 million years after Earth formed, and much of that time, Earth was still being heavily bombarded by asteroids. Once conditions became stable enough for life, life appeared rather quickly in geological terms. This suggests that the origin of life might not be incredibly rare or difficult. If conditions are right, life might arise fairly readily. Fifth, once life appears, evolution seems to lead to increasing complexity over time. On Earth, we went from simple single-celled organisms to complex multicellular life to intelligent tool-using species. This took billions of years, but it happened. Now combine these observations. Old universe, lots of stars, lots of planets. Life might arise readily, intelligence might evolve given enough time. The universe should be full of alien civilizations. Some of them should be far older than ours. Earth is a relatively young planet in a relatively young solar system. There are stars in our galaxy that are billions of years older than our Sun. If those stars have planets, and if life arose on those planets, then those civilizations could be billions of years more advanced than we are. What would a civilization billions of years more advanced than us be capable of? It's hard to even imagine. A few hundred years ago, we were using horses for transportation and candles for light. Today, we have spacecraft, computers, the internet, genetic engineering, artificial intelligence. Extrapolate that rate of progress forward another few hundred years, and we'd have technologies that would seem like magic to people in the past. Now imagine a civilization with millions or billions of years of advancement. They might have technologies that are literally beyond our comprehension. They might be able to manipulate matter and energy at fundamental levels. They might be able to travel between stars routinely. They might build megastructures that we could detect from Earth. Dyson spheres or swarms, structures that surround stars to capture all their energy output. Ring worlds, artificial habitats wrapped around stars, stellar engines that move entire star systems. Such structures would be detectable. A Dyson sphere would block the visible light from a star, but would glow in infrared as it radiates waste heat. We've searched for such signatures and found nothing conclusive. Advanced civilizations might also communicate using radio waves or lasers. They might intentionally broadcast signals to announce their presence. Or we might detect their communications with each other, signals leaking into space. We've been searching for such signals for decades through projects like SETI, Search for Extraterrestrial Intelligence. We've found nothing. No obvious artificial signals, no evidence of megastructures, no alien spacecraft visiting our solar system, nothing. The universe appears empty. This is the Fermi paradox. The universe seems like it should be full of alien civilizations, but we see no evidence of them. Where is everybody? There are many proposed solutions to the Fermi paradox. Maybe life is actually incredibly rare, much rarer than our calculations suggest. Maybe Earth is special in some way that makes life possible here but not elsewhere? Maybe intelligent life is rare. Perhaps intelligence rarely evolves, even when simple life is common. Maybe civilizations exist, but they're not interested in communicating or expanding. Perhaps they're content to stay home, or they've moved beyond physical existence into virtual realities. Maybe civilizations exist, but they're hiding deliberately, trying not to be detected for reasons we don't understand. Maybe the distances between stars are just too vast for communication or travel to be practical. Maybe civilizations rise and fall too quickly to overlap in time and space. Or maybe there's a great filter, something that prevents most civilizations from reaching the stage where they become visible to others. The great filter could be anywhere along the evolutionary and technological development path. It could be the origin of life itself. Maybe life arising from non-life is incredibly unlikely, a 1 in a trillion chance event. If so, then Earth might be one of only a few places in the observable universe where life exists. The filter would be behind us, and we'd be safe. The filter could be the evolution of complex cells. On Earth, simple bacterial cells existed for about 2 billion years before complex cells with nuclei evolved. This was a major transition, and it might be incredibly rare. Perhaps most planets have simple bacterial life, but never develop complex cells. The filter could be the evolution of intelligence. Earth has had complex multicellular life for about 600 million years. During all that time, intelligence comparable to humans evolved only once, in our lineage. Many other species have evolved sophisticated behaviors, but only humans developed language, abstract thought, and technology. Perhaps intelligence is an evolutionary fluke that rarely occurs. The filter could be technological. Maybe any civilization that develops technology eventually destroys itself. Nuclear weapons, biological weapons, AI, nanotechnology, environmental destruction, take your pick. Technology gives civilizations enormous power, and with that power comes risk. One major mistake, one war, one accident, and the civilization could be wiped out. The filter could be something we haven't thought of yet. Some cosmic threat or technological dead end that becomes apparent only after a civilization reaches a certain level of advancement. Here's why this matters and why it's terrifying. If we eventually find evidence of alien life, even simple microbial life, it tells us something about where the great filter is. If we find simple life on Mars or Europa or Enceladus, places in our solar system where we think life might exist, that would be exciting. It would mean life arises fairly easily, given the right conditions. But it would also mean the great filter isn't the origin of life. The filter must be somewhere else, either in the evolution of complexity and intelligence or in technological development. That would be bad news because it would mean the hard part isn't behind us. If we find complex multicellular life, that's even worse. It means the filters of origin of life and evolution of complexity are both behind us. The great filter must be intelligence or technology. If we find evidence of intelligent civilizations, past or present, that's the worst news of all. It means all the evolutionary hurdles can be overcome. Life arises, becomes complex, becomes intelligent. The filter must be technological. Something happens to advanced civilizations. They destroy themselves or they're destroyed by something. And we're heading toward that same fate. This is called the Great Filter Problem, and it's one of the most disturbing implications of the Fermi paradox. The more common life turns out to be, especially intelligent life, the more dangerous our future looks. There's a concept in physics and philosophy called the anthropic principle. It essentially says that we observe the universe to be compatible with our existence, because if it weren't, we wouldn't be here to observe it. It's a tautology, but it has implications. The fact that we exist and we haven't encountered aliens yet could mean we're early, we're among the first civilizations to arise in the universe. If that's true, then the Great Filter is likely behind us. The early universe was hostile to life. It took billions of years for the first stars to form, die, and create heavy elements. It took more billions of years for planets like Earth to form. Perhaps we're living at the earliest time in cosmic history when intelligent life can arise. We might be first, or among the first. If so, the universe will eventually be full of civilizations, but we're pioneers. That would be good news because it means there's no Great Filter ahead waiting to destroy us. But if we're not early, if civilizations have been arising for billions of years and we're typical, then the silence of the universe becomes ominous. Where are all the civilizations that should have arisen before us? The most disturbing answer is that they're all dead. They all hit the Great Filter. They all destroyed themselves, or were destroyed. And we're next. Think about how unsettling this is. The universe might be full of dead civilizations, ruins of once great societies scattered across billions of planets. Perhaps every few million years, on some random planet, intelligence evolves. A civilization arises, develops technology, reaches toward the stars, and then, suddenly, catastrophically, ends. Maybe they destroy themselves in a nuclear war. Maybe they create an AI that wipes them out. Maybe they engineer a pathogen that kills everyone. Maybe they alter their environment so drastically that it becomes uninhabitable. Or maybe there's some cosmic threat we don't know about yet, something that becomes dangerous only once a civilization reaches a certain level of technology. Whatever it is, it kills them before they can spread beyond their home planet. And because space is so vast and timescales are so long, the ruins of these civilizations have decayed by the time the next civilization arises. We wouldn't see any evidence of them. They existed, they thrived, they died, and they were forgotten. The universe doesn't care. It continues its slow evolution, indifferent to the tragedy. And now, we're approaching the same threshold. We have nuclear weapons. We're developing artificial intelligence. We're altering our planet's climate. We're creating synthetic organisms. We have the power to destroy ourselves, and we're rapidly developing even more powerful technologies. Are we approaching the Great Filter right now? Is this the next few decades or centuries, the critical period where we either survive and become a spacefaring civilization or destroy ourselves like countless others before? Us? We don't know. And that uncertainty is terrifying. Because if there is a Great Filter ahead of us, if civilizations really do tend to destroy themselves, then we need to figure out what the danger is and how to avoid it. But we might not have much time. The threat might already be upon us. We might be living in the critical period right now, the time when our civilization's fate will be decided, and the silence of the universe offers no comfort. It might be telling us that we're alone, which would be wonderful. Or it might be telling us that we're doomed, that every civilization reaches this point and fails, and we'll be no exception. This is the nightmare scenario of the Great Filter. We're standing at a threshold that countless civilizations have stood at before, and none of them made it through. We're looking up at the stars, seeing silence, and realizing that silence might be a warning, a tombstone for civilizations past, and a prophecy for civilizations present. So where does all this leave us? We've explored rogue black holes wandering through space, vacuum decay that could destroy the universe in an instant, cosmic rays bombarding us constantly, solar storms that could cripple civilization, mysterious fast radio bursts from unknown sources, galaxies consuming each other, including our own eventual merger, the accelerating expansion of the universe that might tear everything apart, and the terrifying possibility of the Great Filter waiting ahead. These aren't hypothetical science fiction threats. They're real phenomena, observed and studied by scientists. Most of them are unlikely to affect us in the near future. Rogue black holes are rare and space is vast. Vacuum decay might never occur. The Big Rip is billions of years away, if it happens at all. But the point isn't that you should be terrified right now. The point is that the universe is genuinely dangerous in ways most people never consider. We live on a fragile planet, protected by an atmosphere and magnetic field, orbiting a relatively stable star in a relatively quiet region of a stable galaxy. We've been lucky. Earth has been habitable for billions of years, long enough for life to evolve and for intelligence to emerge. But that luck isn't guaranteed to continue. Cosmic threats are real. Some we can potentially defend against, like asteroid impacts, where we're developing technology to deflect dangerous asteroids before they hit Earth. Some we can prepare for, like solar storms, where we can harden our infrastructure and develop warning systems. But others are completely beyond our control. We can't stop a rogue black hole, or prevent vacuum decay, or avoid cosmic rays. We simply have to accept that we exist in a universe that contains genuine threats, and perhaps that's the real lesson here. The universe is not designed for our survival. It's not safe or comfortable or even neutral. It's a place where unimaginably powerful forces operate according to physical laws that don't care about us. We exist in spite of these threats, not because of any cosmic protection. Understanding these dangers gives us perspective. The problems we face on Earth, climate change, political conflict, economic inequality, these are serious and we should address them. But they're also problems we can potentially solve. They're within our control, at least in principle. The cosmic threats we've discussed tonight are not within our control. All we can do is try to survive long enough to become a spacefaring civilization spread across multiple worlds. If humanity remains confined to Earth, we're vulnerable to any number of cosmic threats. A single catastrophic event could wipe us out. But if we establish self-sufficient colonies on Mars and the Moon, and in space habitats throughout the solar system, then we're much harder to destroy. No single event could wipe out all of humanity. Eventually, spreading to other star systems would make us even more resilient. That's the long-term survival strategy. Become a multi-planet species, then a multi-star species. It's the only way to ensure humanity's long-term survival against cosmic threats. But that's a goal that will take centuries or millennia to achieve, and in the meantime, we're vulnerable. So yes, the universe is terrifying when you really understand it. It's full of phenomena that could destroy us without warning. But it's also beautiful and awe-inspiring. The same physics that produces rogue black holes and vacuum decay also produces stars and planets and life. The universe is violent and dangerous, but it's also creative and generative. We're part of that universe, products of billions of years of cosmic evolution. We're made of atoms, forged in stars, assembled on a planet that formed from the debris of earlier stars, animated by chemical processes that emerged from Earth's environment. We're the universe becoming aware of itself. And that's remarkable. So when you look up at the night sky, remember what you've learned tonight. Space is not empty and peaceful. It's full of energies and forces that dwarf anything we experience on Earth. Rogue black holes might be wandering nearby. Cosmic rays are passing through you right now. The sun could produce a civilization-ending storm tomorrow. Our galaxy is consuming smaller galaxies, and will eventually merge with Andromeda. The universe itself is expanding faster and faster toward an uncertain fate, and somewhere, perhaps, the great filter is waiting. But also remember that humanity has survived for hundreds of thousands of years despite all these threats. We're still here. We're still looking up at the stars and trying to understand them. That persistence in the face of cosmic dangers is something to celebrate. We are, in many ways, living in the most dangerous period of human history from a cosmic perspective. Not because cosmic threats have increased, but because we've become aware of them. Our ancestors lived under the same sky, exposed to the same cosmic rays, vulnerable to the same solar storms and asteroid impacts. But they didn't know. They couldn't detect rogue black holes, or measure vacuum decay probabilities, or calculate the odds of a nearby magnetar flare. Ignorance was, perhaps, bliss. We now have the knowledge to understand how precarious our existence really is. We know that we're living on a small planet, orbiting an average star, in an average galaxy, in a universe that contains trillions of ways to die. We know that invisible particles are constantly bombarding us. We know that the sun could produce a civilization-ending storm tomorrow. We know that somewhere in the galaxy, black holes are wandering through space, potentially on collision courses with solar systems like ours. We know that the fundamental laws of physics might be unstable, that the universe could literally rewrite itself out of existence in the time it takes to blink. We know that if we're not alone in the universe, the silence of space might be telling us something terrible about our future. This knowledge is both a burden and a gift. It's a burden because we have to live with the awareness of these threats, knowing we're powerless against most of them. But it's also a gift because knowledge gives us the chance to prepare for what we can prepare for, and to appreciate how remarkable it is that we exist at all, given all the things that could have killed us, but haven't. Earth has been hit by asteroids before, and it will be hit again. But now we have the technology to detect dangerous asteroids years or decades in advance. We're developing spacecraft that could potentially deflect an asteroid away from Earth. The DART mission in 2022 successfully changed an asteroid's orbit by crashing into it, proving that asteroid deflection is possible. We can't stop the sun from producing solar storms, but we can monitor the sun constantly and prepare our infrastructure to withstand storms when they occur. We're building better forecasting systems, hardening power grids, and developing protocols to protect critical systems during geomagnetic storms. We can't prevent cosmic rays from hitting us, but we understand the risk, and we factor it into safety calculations for space missions and aircraft operations. We're developing better radiation, shielding, and medical countermeasures for long-duration space missions. We can't control black holes or magnetars, but we're mapping the galaxy, identifying potential threats, and studying these objects to better understand their behavior. Knowledge won't save us from every threat, but it gives us a fighting chance against some of them. And perhaps most importantly, knowledge drives us to expand beyond Earth. The ultimate defense against cosmic threats is not to be confined to a single planet. If humanity remains on Earth, we're vulnerable to extinction-level events. A large enough asteroid, a nearby supernova, a solar superflare, any number of cosmic disasters could potentially wipe us out. But if we establish self-sufficient colonies on Mars, the Moon, and in space habitats throughout the solar system, we become much harder to destroy. No single event could wipe out all of humanity if we're spread across multiple worlds. And if we eventually expand to other star systems, we become essentially extinction-proof. A threat to one solar system wouldn't affect others light years away. This is the long-term vision for humanity's survival, spread across the galaxy, distributed among countless worlds and habitats, resilient against cosmic threats through sheer geographic diversity. It's a vision that will take centuries or millennia to achieve, but it's the only way to ensure humanity's long-term survival in a dangerous universe. In the meantime, we're vulnerable. We're confined to one planet, exposed to cosmic dangers, hoping that we'll survive long enough to achieve that vision of a spacefaring civilization. The threats we've discussed tonight are real, but they're also, for the most part, unlikely to affect us in our lifetimes. Rogue black holes exist, but the galaxy is vast and encounters are rare. Vacuum decay might be possible, but it might also be so improbable that it will never occur during the lifetime of the universe. Magnetar flares happen, but close dangerous ones are infrequent. Solar storms are the most immediate threat, and even those are manageable if we prepare properly. Cosmic rays are a constant hazard, but one we can mitigate to some degree. Fast radio bursts remain mysterious, but there's no evidence they're dangerous at the distances we observe them. Galaxy collisions happen over billions of years, giving us ample time to adapt or relocate. The expansion of the universe and the potential Big Rip are tens of billions of years away, if they happen at all. And the Great Filter, well, that's the big unknown. It might be behind us, meaning we've already overcome the hardest challenges, or it might be ahead, meaning we have difficult times approaching, or it might not exist at all, meaning the Fermi paradox has some other explanation. We don't know, and that uncertainty is uncomfortable, but uncertainty is part of existence. We've always lived with uncertainty about the future. Our ancestors didn't know if they'd survive the winter, or if the harvest would fail, or if they'd be struck by disease. They lived with constant uncertainty about their survival, and they persisted anyway. We're no different. We live with uncertainty about cosmic threats, about climate change, about technological risks, about whether humanity will survive another 1,000 years. But we persist. We continue to explore, to learn, to build, to create. We continue to look up at the stars and wonder about our place in the cosmos. And that persistence, that drive to understand and to survive, is what makes us human. The universe is terrifying when you really understand it. It's full of phenomena that could destroy us without warning, without malice, without even noticing we existed. But the universe is also the only home we've ever known. We're part of it, products of billions of years of cosmic evolution. We're made of atoms forged in the hearts of stars, assembled on a planet that formed from the debris of earlier generations of stars, animated by chemical processes that emerged from Earth's environment. We're the universe becoming aware of itself, thinking about itself, trying to understand itself. And that's extraordinary. Thank you for spending this time with me tonight, exploring the terrifying side of space. If you found this exploration valuable, please consider liking this video and subscribing to the channel. It helps me continue making these deep dives into the cosmos. And remember, the universe might be dangerous, but it's also our home. We're part of it. And understanding it, even the frightening parts, helps us appreciate how remarkable our existence really is. Sleep well tonight, if you can, knowing that you're living in a universe full of wonders and terrors beyond imagination. Good night, and keep looking up at the stars, even knowing what might be lurking in the darkness between them.